Welcome back, and today we're looking at our first example of doing a Fourier series. So we're starting off with a pretty simple example. We looked at this same function in the even-odd function video. So step A wants us to sketch the graph of the given function for 3 periods. Okay, well let's find out what a period is. Well, for this case, it's saying we go from negative L to L. So that tells us our period is 2L, right? We have 1L in both directions. And then we go L, the length is just going to be half of the period. So it's just going to be L for this problem. So let's go ahead and graph it. Let's sketch it. Sorry, sketch. Can it be straight? Thank you. Oh my lord. Okay. That works. Let's go ahead and sketch it. It will look something like... It's negative x, right? So it's just going like this through the origin. And then it kind of picks back up. Like this. And then we need one more. Yeah. Okay. You get the idea. It kind of goes like this. And like this. Okay. So then we have L, 2L. I guess I should, well, if I want to do 3 periods, we got to go out more. Sorry, that's not L. This is L. L. 2L. Oh, I already did have 3 periods. I was wondering. I was like, what am I doing? Yeah, that's 3 periods. This is 1, 2. Yeah, okay. Negative L. Negative 2L. You can see how they all kind of supposed to line up, you know, here. But what we're going to do now from now on is we're just going to, for part B, we're going to look at this one singular period right here, from negative L to L. Okay? So, part B, well, let's take a look at this before we move on. To help ourselves for part B, right? We know what the form for Fourier solution is. We know it's a cosine term, sine term. Remember how we did our even and odd stuff? Well, that's what we're going to look at. By looking at this, we can see it's symmetric about the origin, so we have an odd function. Odd function. That tells us that, we know it's odd, right? Because it's negative x. Well, it's just x. That's always, x is always odd. So then we know it's an odd function by looking at the graph as well. You can also just look at the function and be like, oh, it's odd. You don't even have to graph it, you know? But it's good to graph it. Odd function, so then we know if it's an odd function, we're going to have a Fourier sine series, right? Why is it a Fourier sine series? Well, let's go through, just for this one, I'm going to show you why it's a Fourier sine series. You can go through it yourself and you'll see that it will be. But let's start with the general solution here. Right, well, our general form for Fourier series, not the general solution. n pi x over L plus b sub n sine n pi x over L. I can tell you off the bat, this is 0 and this is 0. Because a sub naught is what? Negative L, well, 1 over L, negative L to L of f of x d of x. Integral of an odd function is always 0. A sub n, we have 1 over L, negative L to L. This is part B, by the way. Oh yeah, I'm having brain farts. I'm thinking ahead too much. And then that a sub n is times cosine n pi x over L dx. And you can see we have an odd function times a even function, which is odd, which results in an odd integral, so then that's 0, right? So that's how I know. So now we have to solve, well, let me just prove why b of n is solvable. It's going to be 1 over L, integral negative L to L. Those are the correct bounds for this problem, by the way. And then we have f of x, which is negative x, times I'm having a brain, oh yeah, okay, I'm having a brain fart again. N pi x over L dx. And as you can see, odd times odd is even. So an integral of an even function is unfortunately solvable, right? So we have to solve it. So let's go ahead and do our integration now. And look, we're already on part B. We're moving along. So you can do this one of two ways. You could multiply the whole thing by 2 and then only integrate over half the period because it is symmetric, right? It's even. You can do that for any even function, right? So this would be over an even period. So then this would be 2 over L, 0 to L, negative x sine n pi x over L dx. This is our good old integration by parts, right? So we have a product here. So remember, it's uv minus v du, in case you forgot. Integral du, right? Wait, uv minus integral v du. I'm surprised I still remember that after all these years. Okay. Well, it hasn't been that long. It's only been like 2 years. Okay, so then our u would be, oh, our u, remember, it goes, what, Lipet? I'm trying to remember now. Logs, inverse trig, polynomials, exponentials, trig. So we see we have polynomials is going to be before trig. So then u is x. And our du would be dx. Now our our dv would be the other term. N pi x over L. And then our v would be the integral of that. So that's negative L over n pi cosine n pi x over L, right? So now let's plug those in. uv x times, so let me do it this way. Now, wait a minute, I forgot the, and you can pull out the negative sign too, right? We could do that too. So now let me write it this way, because this is getting a little bit lengthy. Not too bad though. X times v, so it's negative Lx over n pi cosine. Remember, we still have to evaluate this over the bounds. This is 0 to L, right? Then go plus. It's what? It's minus, yeah. So it's so that this negative. So you can see, I mean, this negative here and this negative here will cancel. So then we're gonna be left with plus L n pi over n pi times. Oh, this will still be the integral. 0 to L, our bounds, cosine n pi x over L times dx. Just making sure I have it right. Okay, now let's just go through and evaluate. Hope I don't mess up anywhere. So negative 2 over L. Let's see, plug in L for x here. This would be negative L squared over n pi times cosine. It's just n pi, right? Because the L's will cancel. If we would plug in a 0, that would go to 0. So that term I don't even have to write down. Now you'll notice something. If you watched my previous video when I did some simplifications, you will already see. You will see something ahead of time here. So now the next section, the next half, we have to integrate. So let me write this out. That becomes what? Sine? Well, L over n pi times sine n pi x over L from 0 to L. So then we keep going. Negative 2 over L times negative L squared over n pi cosine n pi plus L over n pi. Well, let's distribute this in. Let me think about it. So if x is L, that's L squared. Oh, this is all squared. If L's in there, this is just n pi. Very nice. See, I'll get to it in a minute. But I see something here. Okay, so then that's that, because sine of 0 is what? 0. So then we can distribute that negative 2 over L in. This will be 2L squared over, oh, that's it, n pi times cosine n pi plus, minus 2L over n squared pi squared sine of n pi. Now if you watched I need another page. If you watched my last video when I did some simplifications, we know that cosine of n pi is equal to negative 1 to the n, and sine of n pi is equal to 0. So this term goes to 0, and we're left with... Now don't get me wrong, you could absolutely keep it as cosine n pi. Nothing wrong about that. But this is technically the more proper way, I guess, to write it. Because you're not dealing with trig, I suppose. Okay, so now let's take a look. Well, before we do that, the reason why I said I saw something is because when we were up here, at this step here, I guess, yeah, I could have told you right here and then that this was 0. Because it's cosine by itself, it's going to result in a sine, and I know for a fact that any sine, and it's from 0 to L, and I know for a fact, even if it was negative L to L, it would still be 0. Because think about it, whenever you have sine evaluated with an L, it's always going to be 0. No matter if it's sine of negative n pi or sine of n pi, it's always going to be 0. So that's how I know. So you could have stopped right there, you know, and then you could have eliminated that term. So that's just one way, you know, just thinking efficiently. You want to start thinking efficiently with these, especially as they get harder. You'll see what I mean. Whoops. Okay, so now we know b sub n is this now. This is our final form. Can it be simplified anymore? No, right? So we can just write this like this now. We go back to our Fourier series, and we're plugging in stuff. A naught is 0. So we go right to the series. We have 2L over n pi times negative 1 to the n. Remember, this is times, this is sine series. Right? So you see we're left with the Fourier sine series. Now, you can even further simplify this. This is perfectly acceptable, but just know that you can pull any non-n terms out. So then this would be okay? That's a solution right there. Not too bad, right? As you can imagine, the integration will get more involved, depending on the problem. You can only imagine. And the simplifications can get really annoying. You'll see in a minute how you can have different kind of things going on. But hope you enjoyed the video. And I'm looking at the next example we're gonna have, and it's a lot more complicated than one we have right now. Next example is gonna be no symmetry. Yeah, no symmetry, multiple intervals. By the looks of it, 2 different functions and 2 different intervals. Oh yeah, so that'll be interesting to see. Okay. So I'll see you in the next example.